board. Okay, so right now, the domain would be the value of x that we could use for the exponent. And so there's no issue at all with that. We can use any real number for the exponent, right? Because then we would have 3 to whatever that power is. And then that becomes the number that we subtract from the 5. So you're not raising -3 to anything. You're raising 3 to that power, whatever that is, and then subtract it. Okay, so the x can be any real number. Now, there's a way to get the range from this, but we'll worry about that later, because we can get the range of the function by using the domain of the inverse. All right, so we'll do that method. All right, so we want to rearrange this. So I'm going to subtract the 5. I normally would probably skip a couple steps, but I'm not going to do that here. So what we want to do is we don't want this negative. And so dividing by -1, which is going to change the signs over here. So that's why I'm writing this as 5 minus y. Okay. All right, so now we got the exponential base by itself. And so the exponent, this is the base, value. Okay, so we're going to use the log of the value with base 3. That's going to equal the exponent. All right, and it's just a matter of doing all that. Now, if you want to do your distributive property and solve it that way, that's fine. But what I would do, I'd divide by 2 or multiply 1/2. Okay, and then you can now subtract 3 and divide by or multiply the 1/5. Now it's negative. Okay, so I don't have much room here, so I'm gonna kind of do that all at once. So you should wind up with 3/5 minus 1/10, because when you do the 1/5, it's going to be 1/5 times the 1/2 log base 3, and then this is where I'm going to change the variable to the x. Okay, and that's our function's inverse, so that's why I'm using function inverse notation. Okay, now the domain of the log function is we can't log values that are negative, right? And we can't log values of 0 because there's no exponent to base 3 that would cause the result to be 0. So we have to be greater than 0. So 5 minus x has to be greater than 0. Okay, so that means x is going to be less than 5. All right, well, the logarithmic function produces exponents, so the output, the range is going to be all real numbers. And notice the range of the inverse is related to the domain of the function. All right, so the y can be all real numbers. All right, and then here we could have gotten the range by using an interpretation of this process, or we can get the range by looking at the domain of the inverse. So the range, the y's are always going to be less than 5. And if you think about that, we're 5 and we're minusing something that's always positive. So this will never equal 0, so it'll always be a bit greater than 0. So 5 minus 0 would be the minimum or maximum value. So again, you can think of it that way too. So anyway, that's number 1. Now we'll go ahead and do the same thing with number 2. All right, so then we got the g function, and then this time we're going to rearrange the logarithmic function. And so let me make sure I got the right one. I thought I wrote it down. Let me just double check, y'all. All right, yeah, I thought so. Okay, so -3 minus 2/5, and then log, and then the expression for the domain in the log would be 1/3 x minus 2. Okay, so that's what we got. All right. So now we want to get the domain and range of the function in the inverse. Well, here we're logging this value, and that has to be greater than 0. Otherwise, it's not possible. So we can get the domain of the function by putting the domain expression greater than 0. Okay, so then add 2, multiply 3/1. So x has got to be greater than 6. If x is greater than 6, this will become positive, not equal to 0. All right, so the same kind of thing. We're going to go ahead and find the inverse function. All right, so I'm going to add 3, and then I'm going to multiply the reciprocal. All right, so this should become -5/2y plus 3 equals to this log. Okay, so now we got the log expression equal to something. All right, so the log equals whatever the exponent is. So this is the exponent we're going to use. And there's no number written by the g, so the understood base is 10. And then the value is the expression that we're logging. So we got 10 to the exponent equal the value. Okay, so now we got that. Okay, so now we're going to go ahead and add 2, and then the last step will multiply by 3. So right, adding 2. And now when you multiply by 3, be careful because you can't multiply 3 to the 10. Right? Because 10 has an exponent, and so you're going to have to put the 3 right in front unmultiplied to the 10. So multiplying 3, that's going to become 6. This is going to become plus 3 times. Okay, and this is where I'm going to change the input variable to the x. And then now we have our function's inverse, so we use the function notation. Okay, so this would be the inverse. All right, well, there's no domain issue here because the exponent can be any real number. All right, so the domain of the inverse, the exponent can be any real number, so x can be any real number. Okay, and now we can interpret the range like we did with the earlier one, because we're adding whatever this becomes after we use x to the 6. So this is never going to equal 6. It's always going to be a little bit bigger than 6. Right? So you could think of it that way. Sometimes that's possible. But even if you didn't think of it that way, notice the domain of the function is the range of the inverse. And the same thing here. The range of the function is the domain of the inverse. So this could equal any real number because logarithms are exponents, and an exponent can be any real number. Again, just different ways of thinking about this stuff. Okay. Ugh, I'm a little sluggish this morning, or today rather. It's like thinking, oh, God, do I have it? Ah. I guess we'll find out. You all okay? Is that anybody want to ask anything?
Mr. Napoli?
Yeah?
So like the test that we took before school closed,
Uh-huh.
is there any way we're going to be able to retake those tests?
Well, you have to email me and ask.
Okay.
That's how I've been handling it, I mean, some students that may not be an issue. Some students it is. We had asked. You just asked. Okay? Just shoot me an email. We'll work it out. It's not the best situation. What are we going to do?
Mr. Napoli, can you say one more time why it can't be less than 0? Because I'm blanking out right now. why the value of a log can't be less than 0.
Okay, because the log is going to get us an exponent, right?
Yeah.
All right. So if we're going to apply an exponent to a positive number, is that going to produce a negative value?
No.
No,
Oh, okay.
right? And so we know this can't be negative. But the same idea applies if you're trying to get 0. You can't apply an exponent to a positive number and get 0 either.
Okay.
Right? So that's a good question. We're going to look at that today when we look at making graphs of these things. But that's why this is always greater than 0.
Okay.
Okay, anybody else want to get any clarification? Or yeah, this is stuff that's important because it's used in the sciences a lot. In fact, they have what are called log graph paper, which I think we're going to look at probably the last day. It's important to know. We'll see. We'll just see. But again.
Oh, Mr.
Yep.
Napoli, could you have like a base of a log as a negative number?
A base of a log?
Yeah. Like the log base.
No. I mean, theoretically you can, but
Okay.
we don't do that because then it's going to involve having to take roots of negative numbers.
Oh, okay.
Right. So if you have, like, say you have a 1.267544441 exponent, that essentially is the root. And so when we start getting in the roots of negative values, that becomes problematic.
Yeah.
So that's why we only use positive bases. I mean, theoretically, there's nothing wrong. I mean, if you do, you have to deal with imaginary numbers, which is actually what people do when they're using that theoretical application. But in general, no, we always have positive numbers for bases. Okay, anybody else want to ask some thought-provoking, genuine question? All right, y'all. Okay, so, I forgot what I was going to do. Well, if we're looking at logarithms, we're going to look at graphs of logarithms. So remember, logarithms are going to give you exponents. All right, that's what their purpose is. So let's say we make some basic graphs of logarithms and see how they compare and what the graph looks like. So, okay, at y-axis, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, we'll end that way. And so depending on the base, the exponent necessary might be bigger or smaller than if you use another base. Okay, so if we're going to do something like y equals log using base 2, well, if you use a value of 1, so when the value is 1, this is going to need a 0 exponent because you'd have to do 2 to the 0. So the y will be 0 when x is 1. All right. Now, as we go to the right, the values are getting bigger than 1. And so when we take the log of the values that are bigger than 1, we're going to start needing exponents that are bigger than 0. So if we have 2 to the first, then when we log the 2, we'll need a 1 exponent. So the 1 will be right there. Well, what's the next time we have an exponent that's an integer? Well, that would be when it's 2. So when does this equal 2? Well, that would have to be when we have a value of 4. So now this is going to be here at 4. Right? And then the next thing would be 2 to the third power. So the next integer exponent, the next integer result of the log is 3. And that's going to happen at 8 to the third power. And then that's why I put 16, right? Now, I don't know if my graph is lining up here. It might not. But you get the idea. All right, so then the next integer exponent, the next integer output of this log is 4. And that's going to happen when we have 2 to the fourth, which is 16. Okay, so if we're just dealing with values that are 1 or greater, that's it. All right, now once we start having values that are less than 1, so once we start having values that are between 1 and 0, that's going to be fractions, right? So the next time we have a negative exponent of -1, that's because 2 to the -1, which is a half. So that would be right about here. And then the next integer exponent would be -2. That would be when we have 2 to the -2, which is 1/4. And that would be right here. And then the same thing. So then this would be to the -3, which is 1/8, and then 1/16, and then 1/32, and then 1/64, and then 1/128. So this is shrinking because this is gradually becoming, and whatever the negative exponent is, right? And so that's why this is happening. Now it's never going to get to 0 because that means you could get a value of 0 by applying an exponent. So this is the vertical asymptote, right? And if you remember the exponential function, which was like this, it was a horizontal asymptote, right? This would have been 2 to the x. And so 2 to the x points up, the log of the x points to the right. 2 to the x is a horizontal asymptote. The log of the x has a vertical asymptote. Okay, remember these 2 to the x and logarithmic, these are inverses, right? Okay, so that's how these are related. All right, and notice that the interval between 1 and 0, that's where we need negative exponents. Okay, so that's why this curve is dropping below the x-axis, because once we're in between 1 and 0, we're going to need negative exponents. And that's going to be true all the way until the very smallest possible number that is just a little bit bigger than 0. Right. All right, well, what if we had a different base? Let's say we had, and I'll just do this in blue, let's say we had log using base 10. Now, you don't really have to write the 10. I just want to make explicit. Well, 10 to the 0, that's still 1. So this location isn't going to change if we have a base 10 instead of a base 2. Because to get a value of 1, you're going to need a 0 exponent. 10 to the 0 is 1, so is 2 to the 0. So any base to the 0 power is going to always be 1. So the log of 1 is always going to be 0, regardless of the base. But this one has a different scale as it goes through the exponents like we did earlier. So now instead of having to go to 2, base 2, 2 to the first, now we got to go all the way here to 10. Base 10, 10 to the first. And so that's where that goes. All right. So notice this is pulling farther away from the vertical because 10 is 5 times bigger. Right. And so it's true we're not going to go to 100. That's way the heck over there. That's halfway down the block. But that do the same thing. Now what happens here? What about between 1 and 0? Well, it's still going to be reciprocals. So 1 over 10, 1 over 100, 1 over 1,000, right? So 10 to the -1, 10 to the -2, and then I didn't put -3. All right, well now, when it's a -1 exponent, that's 1/10, which is less than 1/2. So that's going to go much closer to the vertical asymptote. Okay, so that's the relationship. Now E, which would use the ln, if we had e to the x, E is in between 2 and 10. So if we used E, it would still start at the same place, the x-intercept of 1, because E to the 0 is also 1, but it's not going to rise as fast as 2. And since it's in between 2 and 10, this graph is basically going to go in between. All right, and e to the first power would be 2.7 something. So that would be right about here. Okay, and then again, e is less than 10. So the reciprocal of 10 is smaller than e, the reciprocal of e. And the reciprocal of e is smaller than the reciprocal of 2. So e would be in between these two. So if we did the ln graph, it would be in between the 2 and the 10. And same thing here. But all of these graphs are going to intersect the x-axis at 1, because when you use a 0 power, it's always a result of 1, regardless of the base. So that's the basic graph. We have a vertical asymptote at 0. Okay, anybody want to ask any questions for that before we look at transformations? Okay, and again, if you want to think about it, if you're, some people have thought processes at work, you could think of it as the inverse of this, right? So switching the x and y. Horizontal axis switches vertical axis, right? Goes up to the positive y, switches, goes right to the positive x. So I don't know if that works, but you can think of it that way. All right, well, let's look at least 2 of these transformations and coming up with the graphs of the transformations and then determining where the new vertical asymptote may or may not be. All right, well, the first thing, when we did the exponential, the horizontal asymptote only changed if we went up and down. Otherwise, it was always y equals 0. So if you didn't have a vertical transformation with an exponential function, then the horizontal asymptote would remain y equals 0. Okay, well, with log functions, it's a vertical asymptote. So this will always be x equals 0 unless you move left or right. So you have to have a horizontal translation if the vertical asymptote of a log function is going to change. So if there's no horizontal transformation, the log function's asymptote, the vertical asymptote, is always x equals 0. Okay, so let's look at a basic one. So let's say we had this. Okay, well, the parent. And then notice we're changing the sign of the domain x and the result output y. So reflection across the y, reflection across the x. Okay, so there's no translations. So the vertical asymptote is going to stay the same. Okay, so the parent function, here's where 1 is. And our vertical asymptote at x equals 0. And then once we take logs of values greater than 1, it's going to do that. Okay, so now we want to flip this over the x and y axis. It doesn't matter what order. So let's say you flip it over the y-axis first. Well, now we're at -1. Now we're doing this. So flip it over the y-axis first. All right. Now flip over the x-axis. Okay, well, now we're going to flip over the x-axis, so it does this. Okay, and in this case, the vertical asymptote didn't change, so it's still y equals 0. Okay, now this left side here, that's getting slowly bigger. It's not linear. It's not approaching anything, right? Because again, that came from the exponent 1, 2, 3, 4, 5, if you remember, right? So the exponent of 1, and then the exponent of 2, then the exponent of 3, and then it will always slowly keep getting bigger. So this doesn't approach any constant value. It's the vertical asymptote, not this. All right, let's do one that has these transformation issues. All right, So let's say we had okay, well now we do have a horizontal translation. All right, and notice we're minusing a log, so that means we're multiplying by negative. So that's going to change the sign of the output. So changing the sign of the y, reflection across the x, and we also have a vertical translation. All right, so you do the translations last. We don't have a number multiplied to the x. We're not multiplying to the log, so we don't have any domain or range dilations. All right, so the parent. Okay, and then we're changing the sign of the log, so that's reflection across the x. And then you can either do horizontal translation first or vertical translation first. I'll do the horizontal translation first. So -2. Because again, to get back to the 0, you have to go to -2. All right. So notice the horizontal asymptote is shifting to the left, not to the right. I mean, vertical asymptote. All right, and then vertical translation +5. Okay, so we got the parent. And, you know, we're just sketching the graph, but if you wanted to do a little bit of a scale, you could do this other point over here at 10. So if you want to do that, you can do that. All right, reflecting across the x. So we're going to flip it like that. I'll do that in green. And then right. Okay, now we're going to move this to the left 2 and up 5. So this point right here is going to go to the left 2. It's going to be at -1, and then it's going to go up 5. All right. Our vertical asymptote used to be at 0. We're going to the left 2, so now it's going to be at -2. All right, and so now we got, well, let me do that in blue. Let me make that easier. Okay, and if you want to move this point -1, 10, we're going to go left 2 up 5. So if you have -1, 10, and you go left 2 up 5, you'll be at -3. Oh, wait, I'm sorry, y'all. I realized I switched the x and y. 10, -1. Okay, so we're going to go left 2, so -2 from the x. We're going to go up 5, so add 5 to the -1. Okay, so this point that I was using as a second reference point, right? So that came from the original log graph. You need an exponent of 1 when you have 10 to the first. So now that came over here when I did the reflection across the x, so that's why it's -1. The 1 flips to -1. Okay, and now I'm translating this point 10, -1, left 2 up 5. So that's why I'm subtracting 2 from x and adding 5 to to the y. All right, so now this is going to become 8, 4. All right, so then this point right here, you could say is 8, 4. Now that's not the scale. That would probably be up here, you know, because the 4, but anyway, that's basically the shape of the graph. Okay. All right, now, if this was multiplied by 2, then from the location that was originally on the x axis, it's going to pull up and down. It's going to pull farther away from the horizontal. If, however, there was a 2 here, and let's make this a 4, so it still has the same horizontal translation. Well, now this is a domain dilation, so that's half as much. So that's going to squeeze the graph closer to the vertical. It's going to have the same effect. Notice this is pushing closer towards the vertical. It's half as much x as it was before. Now, keep in mind, this point right here was originally on the x-axis, right? So it's going to be right about here. Okay? All right, that's basically all I got for y'all today. I don't think you really have these domain range dilations issues on the homework, but I just, it's important to be thorough. Anybody have any issues about anything?
When you're applying the 2 in front of the x, or sorry, a 2 in front of the log,
Right.
Could you like show us how that would affect points? Like the same way you did the horizontal and vertical translations with the point. Can you do that with the multiplication?
So you want me to do this problem more thoroughly? Is that what you're saying?
Yeah.
Okay, no problem. So you want to save the translations for last. So then we will do the range dilation here first. Okay, so that would be range dilation times 2. Whereas if I put the 2 here, that would be domain dilation times a half. All right, so we got our parent function. So that's 1 here. Okay, we flip across the x-axis. So that's here. Okay, now here, right here, that would be, let me see, 5 minus 2 log of x. So we haven't done the horizontal translation yet, right? So now we're just multiplying to the y's. So that's not going to change because 2 times 0 is always 0. Right? So now we're going to have double as much y for the same x. All right, so then that's going to have this effect. Right, so again, we're talking about 2 times the log at x, right? So originally it wasn't doubled. It was the same log x. Now it's twice as much. Where'd my, shoot, didn't I? Okay, there it is, sorry. All right, so that means, say here, this is 3. Well, before we multiplied to 2, that would have been here. But after we multiplied the 2, we're going to subtract much more from the 5. So that's now here. Right? And you
Okay, that makes more sense.
Okay. Glad
Thank you.
asked. Yeah, no problem at all. I'm glad you asked. Does anybody else have anything they need a little clarified? Darn it. All right, that's all I got for y'all today. So basically, you're just going to be finding inverses of exponential and logs and then making graphs like this. That's all the homework is. All right, y'all take it easy.